While the world celebrates the complete liberation from worries about the third interstellar traveler in history, the Tri-Eye Atlas, another troubling event unfolds in the shadows, of which we have just learned. A comet, bubbling with emissions, approaches Earth's orbit much closer than we would like. She slipped away from our telescopes until the sun revealed her. On October 20th, 2025, just 8 days from now, she will reach her closest approach to Earth. What does this mean for us? Is this a real threat? Stay with me until the end, and you will understand why the real threat was never the comet mentioned in the news, but one we barely noticed. If these mysteries have captivated you as they have me, don't forget to like to not miss any updates as it all unfolds in real time. Write in the comments where you are listening from, what time it is for you, and whether you believe we are getting the full truth about these world-changing discoveries. And if you want to help our community grow, share this video on social media or just in your group chats. You are the reason we can continue to seek such stories, and thank you for supporting us. The first part. The headline is currently about the three-eyed Atlas. The headlines call him mysterious. Social media is filled with theories, while astronomers struggle to reassure us that it poses no danger. And they are right. The Three-Eye Atlas, this interstellar traveler from beyond our solar system, will fly past Earth at a comfortable distance of 1.8 astronomical units, which is about 167 million kilometers. NASA has clearly stated, there is no threat. The orbit remains far from us, a celestial tourist that will fly by and vanish back into the void. So why are we obsessed with it? Because it came from another place. Because the word interstellar carries a certain magic that makes us forget the practical. We like the exotic guest, the stranger at the door. We forget to check who is already in the house. While the world watches the three-eyed Atlas, another object glides into our neighborhood. Comet C-2025R2, named a swan after the instrument that discovered it, is approaching. On October 20th, 2025, in just 8 days, it will reach its closest approach to Earth. Not 1 whole and 8/10 astronomical units, but 0 whole and 2,066 hundredths astronomical units, about 39 million kilometers. Closer than it seems, and closer than we would like uninvited guests to approach. Let me describe what this comet looks like. R2 was discovered in late September 2025 by an amateur astronomer named Vladimir Bazugli, who was analyzing data from a solar wind measurement instrument aboard the SOHO spacecraft. He wasn't looking through a telescope, he was observing hydrogen emissions glowing in ultraviolet light. Not the usual way to find comets. Ground-based optical observations typically scan the sky, capturing faint points of reflected sunlight. But R2 was invisible to them. He hid in the sunlight, too close in angular distance for telescopes on Earth to see him. This phenomenon is called the Houlichak blind spot effect. Objects in this zone are ghosts. They exist, but we cannot perceive them until they come into the light. The R2 comet appeared on the horizon only after it passed perihelion, its closest point to the Sun, on September 12th, 2025. By the time we noticed it, it was already heading towards us. Perihelion was about half an astronomical unit, approximately 75 million kilometers from the Sun. This is close enough to vaporize volatile substances from its surface, causing eruptions that destabilize its structure. And this happened. At the end of September, observers noted a sharp increase in brightness. The comet suddenly became brighter, reaching a magnitude of about 5.9 or 5.6, depending on the report. Its coma, a cloud of gas and dust around the nucleus, expanded. The photographs revealed a greenish halo, a sign of diatomaceous carbon and cyanogen radicals fluorescing under sunlight's ultraviolet rays. The tail stretched across several degrees in the sky, visible through binoculars if one knew where to look. But here is the thing. We still do not know the size of the core. We do not know its rotation state. We do not know if it has cracked or will crack. Comets are unpredictable beings. They can shed pieces, break into fragments, and disperse clouds of debris along their orbits. And if R2 does any of this, these fragments will slightly deviate from the main trajectory. They will disperse, forming a cloud of potential intersections with Earth's orbit. The minimum distance of orbit intersection, or MOED, between R2 and Earth is approximately 0.48 astronomical units, about 7 million kilometers. In cosmic scales, this is nothing. This is the gap between safety and potential danger, depending on what happens next. I'm not going to claim that R2 will collide with us. Current orbital calculations say that won't happen. But I want to say that our inability to see it earlier is the real risk. We created a detection system that works well for objects in the right part of the sky, with the right brightness and at the right time. But if an object is hidden in sunlight or comes from an unexpected angle or suddenly becomes brighter when we have already looked away, we miss it. We missed R2 until it was almost in our path. How many others did we completely miss? It's not about panic. Panic is useless. It's about paying attention to what almost always slips from our view. It's about realizing that the most frightening objects are not the ones that make the headlines. They are the ones we don't see until it's too late. The three eyes of Atlas are just a side effect. This is the hand of the illusionist waving in the air while the trick happens somewhere else. R2 is indeed that trick. So, here's what we are going to do. First, we will break down the distraction with Atlas's three eyes and show you why it's safe. Then we will delve into what we know and do not know about R2. We will consider scenarios of speculative risk, traces of dust, fragments, and meteoroid swarms. Let's compare this to close encounters that were barely noticed. Objects that slipped past our defenses with a warning just days or hours before. In conclusion, let's discuss what you should pay attention to, what to demand from the institutions that are supposed to monitor these things, and what happens when the detection system fails, because such failures occur more often than you think. And when this happens, the object that slips by is not always the one you were tracking. Part 2. The mechanics of discovery. Why Swan found it, while ground-based studies did not. Comets are usually detected by optical astronomical surveys. Telescopes scan the night sky in search of faint points moving against the stars. These points become brighter as they approach the sun, when their ice sublimates, forming tails. We have been doing this for centuries. It is a reliable method, except when it is not. The comet C-2025 R2 was not found using an optical telescope. It was detected by a hydrogen radiation detector installed on a spacecraft orbiting the sun. This instrument is called SWAN, which stands for Anisotropy of Solar Wind. It is part of the SOHO mission, the Solar and Heliospheric Observatory, launched in 1995. SWAN was designed to image solar wind, detecting hydrogen, calcium, and alpha radiation in the ultraviolet spectrum. Hydrogen glows at a specific wavelength, 121.6 nanometers, invisible to the human eye, but bright in ultraviolet. When comets release water vapor through sublimation, this vapor breaks down into hydrogen and oxygen. Hydrogen spreads in a massive cloud around the comet, significantly exceeding the visible corona. SWAN can see this cloud from millions of kilometers away, even when optical telescopes notice nothing. This is not a new skill. SOHO SWAN has discovered thousands of comets during its operation, most of which are small objects approaching the sun and evaporating in its atmosphere. But R2 does not belong to this category. This is a guest from an outer solar system, probably from the Oort cloud, making a close pass by the sun and then moving back. Its invisibility to ground-based observations was due to its position. It was too close to the sun in the sky. The angular distance was too small. Telescopes on Earth cannot look directly at the sun without being blinded. There is a zone around the sun, a cone of invisibility, where objects simply disappear from our sight. Astronomers call this the Halleck effect or the Coolidge blind spot, depending on which historical figure you prefer. The principle remains the same. Objects in this zone are ghosts. R2 spent its perihelion in this zone. It flew around the sun on September 12, 2025, at a distance of about half an astronomical unit, which is approximately 75 million kilometers. For several weeks before and after this, it was invisible to optical observations. When the object emerged from the bright light, it had already passed perihelion and was moving towards Earth. It was at this moment that Vladimir Bezugli, an astronomy enthusiast, noticed it in the SWAN data while reviewing archival ultraviolet frames in search of characteristic hydrogen glow. He discovered a moving object, a blurred cloud that changed its position over time. He noted it. Other observers verified the data, and optical confirmation followed. The comet turned out to be real, but by then, we had lost several weeks of observations. We had no data on her behavior before perihelion. We didn't know how she brightened, how her orbit developed, or if her disintegration had already begun. The detection system has its strict limitations. Optical surveys have minimal brightness limits, gaps in sky coverage, interruptions due to bad weather, and glare zones. Ultraviolet instruments like SWAN have varying sensitivities and blind spots. They can detect comets that optical telescopes miss, but they are not meant for comprehensive sky surveys. These are specialized instruments, and specialized instruments capture specialized objects. The consequences of late detection are serious. Uncertainties in the orbit above when you have fewer observations. It takes time to refine the trajectory and measure perturbations to account for non-gravitational forces like gas emissions. Our comet was discovered late. Its orbit was uncertain. Even now, weeks later, there are still discrepancies. We have a rough idea of where it's heading, but it's not precise. In orbital mechanics, accuracy is crucial. We also missed early activity. Comets often show activity near perihelion when solar heat causes explosive release of volatile substances. If our comet did this, we did not see it. We do not know if it shed large fragments during this time. We do not know if its core cracked. We do not know the state of its rotation, which affects how it spins and sways under asymmetric forces of ejection. All this information is lost. We act blindly, trying to predict the behavior of an object that we began observing only halfway through its path. This is not a failure of individual astronomers. It is a structural limitation of our detection network. We have optimized the system for specific types of objects in certain parts of the sky. When something falls outside these parameters, we miss it. And we completely miss this until an astronomy enthusiast with access to a cosmic instrument accidentally notices the glow of hydrogen in archived data. How many more comets have we overlooked? How many pass through the solar system now, remaining invisible because they are not in the right place at the right time? We do not know. We cannot know. This is the problem. Next, we will examine what exactly happened to Comet R2 since its discovery. Emissions, oddities, structural features that make this comet something more than just another icy rock. Part 3. What exactly did Comet R2 do? Allow me to guide you through the timeline. On September 11, 2025, Vladimir Bazugli discovered a moving source of hydrogen in satellite images using the SWAN. The object was designated C2 of the 25th year, where 2 indicated the half of the month, and 2 meant it was the second comet discovered during this period. Optical confirmation arrived swiftly. Observers on Earth pointed their telescopes at the specified coordinates and saw it. A blurry spot, a coma, faintly glowing in the pre-dawn sky. The comet passed perihelion the day before, on September 12th, at a distance of approximately 0.537 astronomical units from the Sun. That's close. Close enough to sublimate water ice, carbon dioxide, methane, ammonia, all the volatile substances that comets carry, and the activity truly began. At the end of September, observers reported a sudden increase in brightness. The comet suddenly changed its visible magnitude, with some estimates at 5.9, others at 5.6. The magnitude is measured on a logarithmic scale, so even a small change in number means a significant increase in brightness. The coma was expanding. The photographs showed a greenish halo around the nucleus, characteristic of diatom carbon molecules glowing under ultraviolet light, often seen in comets. Carbon compounds sublimate from the nucleus, ionize under solar radiation, and fluoresce green. It looks alien, but it's just chemistry. The comet's tail demonstrated asymmetries. Some images showed jets, narrow streams of material shooting away from the sun. This indicates localized degassing, likely from active vents on the surface of the nucleus. Comets are not uniform. They are mosaics of ice and stones, with some areas richer in volatile substances than others. As the nucleus rotates, different outlets face the sun, causing bursts of activity. As a result, a tail is formed that changes shape, pulses, and sometimes breaks into several streams. R2 exhibited all these characteristics. Observers also noted significant dust retention. Usually, solar pressure pushes small dust particles away from the comet, forming a smooth tail. But if the particles are large or sticky, they lag behind, creating a blurred cloud that slowly disperses. R2 seemed to produce many large particles. This has its consequences. Large particles mean that the core is shedding large pieces, possibly fragments, perhaps chunks of surface cracking under thermal stress. If these pieces are large enough, they may survive as independent objects, each with its own trajectory. And these trajectories can diverge from the parent comet, spreading a band of debris in space. An especially impressive image appeared on the astronomical picture of the day on September 18, 2025. It showed a greenish comet R2 against the twilight sky with a tail stretching upward, away from the bright light of the hidden sun. The comet was still close to the horizon, making it difficult to observe, but it was undeniable. Astrophotographers captured it, some using binoculars, others small telescopes. Reports describe a tail several degrees long, a ghostly ribbon stretched across the sky. But here's the thing. Predictions of comet brightness are usually unreliable. Comets do not obey simple rules. They can flare up, fade, shatter, and their brightness depends on the area of the surface that actively sublimates, which in turn depends on the size of the nucleus, its composition, rotation speed, and solar heating. We can make reasonable assumptions, but comets love to surprise us. The R2 comet was predicted to reach a magnitude of 4 under optimal conditions, making it well visible to the naked eye from a dark location. Other forecasts are more cautious, suggesting it will remain at magnitude 6, which will require the use of binoculars. As of October 10, 2025, it is reported that the magnitude is about 6.7, which places it just below the threshold of visibility to the naked eye. Whether the brightness will increase further depends on whether a resurgence occurs, and we do not know if it will. The comet's core remains unresolved. Telescopes only see the comet, a glowing cloud of gas and dust. The solid core is hidden inside, too small and too dim to distinguish. We do not know its size. Estimates based on brightness and activity suggest that its diameter is several kilometers, but this is merely a guess. We do not know its shape. We do not know if it is a single object or a collection of fragments loosely connected to each other. We do not know if its splitting has already occurred. Some comets break apart quietly, shedding pieces without dramatic bursts. You notice this later when depicting the comet in high resolution and see several condensations, several nuclei. It's speculative, but worth noting. A splash at the end of September indicates the presence of internal reserves of volatile substances. Something inside the comet has built up pressure and released it forcefully. This could be carbon monoxide ice sublimating explosively. It could have been subsurface pockets of water suddenly exposed to sunlight. It could have been a structural failure, a crack opening and releasing gas. Whatever it was, it happened once and could happen again. And if this happens at the wrong time, when the comet is close to Earth, these pieces will scatter into a cloud of debris that we might fly through. Next, we will talk about the numbers on hard orbital data, distances, speeds, and the geometry that determines whether it's curiosity or a problem. Part 4. Hard figures and verification of orbital reality. Let me introduce you to the geometry. Comet C, divided by 2025 R2, moves in an almost parabolic trajectory around the Sun. Its orbital eccentricity is 0.993,629, which is almost 1, but not quite. An eccentricity exactly equal to 1 signifies a parabola, an open curve that comes from infinity and returns to infinity. An eccentricity slightly less than 1 indicates an extremely elongated ellipse, a trajectory that takes tens of thousands of years to complete. Orbit R2 has a semi-major axis of about 798 astronomical units, meaning its farthest point, aphelion, lies far beyond the Kuiper belt, deep in a cloud of hydrogen. The comet's orbital period is estimated at 22,554 years. It last visited the inner solar system in the late Paleolithic, when people painted on cave walls and hunted mammoths. The tilt of its orbit is approximately 4.47 degrees. This is the angle between the orbital plane of the comet and the ecliptic, the plane of Earth's orbit. 4.47 degrees is a low value. Most comets from the Oort cloud have steep inclinations, entering the solar system at random angles. Comet R2 is nearly flat relative to the planets. This simplifies predicting its trajectory, but also means it spends more time near the ecliptic plane where Earth orbits. This increases the likelihood of close encounters. Perihelion, the closest point to the Sun, occurred on September 12, 2025, at a distance of 0.53400 astronomical units. It is about 75 million kilometers, a little closer than Venus's orbit. At such a distance, solar heat is intense. Surface temperatures can reach several hundred degrees Celsius. The water quickly sublimates, volatile substances turn to gas. The comet's core ejects dust and gas at a frantic speed. It is at this moment that comets begin to glow brightly, becoming spectacular but also unstable. Now we are moving further from the Sun. Comet R2 is moving away from the Sun, but its trajectory intersects Earth's orbital path. On October 20th, 2025, the comet will reach its closest distance to Earth. This distance will be 0.2665 astronomical units, which is approximately 38,992,517 kilometers. This is about 100 times the distance to the Moon. From a human perspective, it seems distant. From a cosmic perspective, it's a close pass. But the key factor is the minimum distance of orbital intersection, the smallest possible gap between Earth's orbit and the comet's orbit, calculated geometrically without considering time. For R2, this value is about 0.048 astronomical units, which is roughly 7 million kilometers. This means that if you draw both orbits in space and measure the shortest distance between them, you will get 7 million kilometers. This is the gap. If the comet and Earth were not in the right place at the right time, that distance could shrink to zero, but they are not there. The current orbital model shows that on October 20th, Earth and R2 will be separated by 39 million kilometers. The comet will pass by, and we will be safe. The model confirms this. The calculations too. NASA is not issuing warnings. There is no signal of a possible collision. So why are we still talking about it? Because orbital solutions are not perfect. They are based on observations, and observations have inaccuracies. The more observations, the better the solution. But R2 was discovered late. We have fewer observations than we would like. The orbit is well constrained, but not perfectly. Small disturbances, non-gravitational forces from outgassing, changes in the mass distribution of the comet, all this can slightly alter its trajectory. A shift of a few thousand kilometers may not matter for the parent nucleus, but it is significant if the comet has shed fragments. Fragments may drift apart. If P2 is damaged, if it has shattered into pieces, those pieces will move at slightly different speeds. Over time, they will spread along the orbit, forming a stream of debris. The larger the fragment, the less it breaks apart. Small fragments, dust particles, pebbles, they can be scattered widely. And if the Earth passes through this stream of debris, we will see an increase in meteor activity, possibly a meteor storm or something even more serious. The current brightness is 6.7 times the value on October 10th, 2025. It's dimmer than expected in the forecast, but not surprising. Comets dim as they move away from the sun. The question is whether there will be another surge of activity from P2. If this happens, if it suddenly sparkles, it will signal a resurgence of activity, possibly fragmentation, perhaps a new release of volatile substances, and this will change the risk level. Visualization helps. Imagine the sun at the center. The Earth's orbit is a circle around it, about 150 million kilometers in radius. Orbit P2 is an elongated elliptical trajectory that comes from the outer part of the solar system, circles the sun, and goes back. The two orbits intersect, but not at the same time. The comet passes through a convergence point in October. Earth goes through it months later. The interval is both spatial and temporal. As long as this is true, we are safe. But comets are unpredictable. They do not follow train schedules. They wobble, crack, and shed pieces, which do not follow the parent's trajectory. They drift, scatter, and sometimes appear unexpectedly. Next, we will talk about the theater of observation, public spectacle, distractions, and how media coverage shapes our attention. Part 5. The nearest theater, observations, the intersection of media, and public distractions. October turns into a crowded sky. Comet C-25 P2 approaches its closest flyby to Earth, peaking around October 20th. But it is not alone. Another comet, C-2025A6, also known as Lemon, brightens and becomes visible in the northern hemisphere around the same time. Two comets, both visible to astronomy enthusiasts, approach Earth within days of each other. This spectacle, this rarity, is what makes people look up. Then comes the meteor shower of the Orionids. The Orionids peak every year around October 20 or the 12th, when Earth passes through the debris of Halley's comet. Yes, exactly Halley's, the famous one that visits our planet every 76 years. Even when Halley is far away, its trail remains, a stream of dusty and icy fragments scattered along its orbit. Every October, the Earth crosses this stream, and particles collide with the atmosphere at 70 kilometers per second, burning up and creating streaks of light, meteors. The Orionids typically produce 10 to 20 meteors per hour at peak moments, sometimes even more. It is not a powerful meteor shower, but it is predictable. Thus, on the night of October 20th, 2025, two comets will be visible in the sky, along with a meteor shower at its peak activity. The sky will be filled. The media will actively cover this event. Astronomy enthusiasts will fill social media with photos. News agencies will publish materials about the celestial show. This is the perfect moment for engaging the public, but it is also the perfect moment for distraction. Because while everyone admires the Orionids, while astrophotographers capture the two comets, while headlines speak of the beauty and wonders of space, very few will ask more complex questions. How close is Comet R2? What is its range of uncertainty? Has it split apart? Are we tracking the debris? What will happen if something unforeseen occurs? The Washington Post covered the event with two comets, noting that both R2 and Lemon would be visible to observers with binoculars or small telescopes. They emphasized the rarity, beauty, and the chance to see two comets at once. But they did not highlight the proximity. They did not mention the minimal distance. They did not discuss the risk of fragmentation. This is not criticism, it is simply the nature of public scientific communication. Spectacles attract attention, risk assessment does not. And then there is the Atlas III, an interstellar alien that continues to make headlines, although it will pass at a distance of 1 whole and 18/10 astronomical units, which is considered a safe distance anyway. The media loves the three-eyed Atlas because he is mysterious. He came from another star system. He is red or perhaps green, depending on which observational information you trust. He changes color or seems to change, which is strange. Asteroids usually don't behave this way. It sparked speculation about its artificial origin, extraterrestrial probes, and messages encoded in its trajectory. Most likely it's not true, but it excites. It's interesting. It's the kind of story that will be actively shared. Meanwhile, R2, a closer guest with an uncertain orbit and history of ejections, receives less noticeable lighting. It is less exotic. This inhabitant of the solar system likely comes from the Oort cloud. There is nothing interstellar about it. It's just another comet, although, in reality, it is not. This is a comet that we did not notice until it was almost in front of us. It is a comet that was hidden in sunlight and appeared only after perihelion. It is a comet that could fragment and may continue to do so. This comet is at a minimum distance of 7 million kilometers, which is quite alarming. Public perception is shaped by novelty. 3 Atlas AIs are new, while R2 is not. Therefore, the 3 Atlas AIs make headlines, and R2 becomes a footnote. But footnotes can be dangerous. Footnotes can hide important things. Behavioral caveats are necessary here. Comets do not always behave predictably. They can unexpectedly brighten. They can unexpectedly dim. They can fragment without warning. Forecasts are guesses based on past behavior, but each comet is unique. Comet R2 may become bright, reaching 4th magnitude, and be a spectacle for the naked eye. It may also dim to 8th magnitude and disappear from view. It may shatter into fragments and create a field of debris. Or nothing may happen at all, and it will quietly return to a distant corner of the solar system. A year from now, it may be forgotten, but it cannot be said for sure. One thing is known. This is not a warning of a collision. Current orbital calculations show that R2 will pass by Earth at a distance of 39 million kilometers. This distance is not close enough for a collision, but it is close enough for other consequences. Close enough for interaction with debris. Close enough to observe the meteor shower. And if the comet unexpectedly breaks apart, its particles might intersect Earth's orbit. This is the nature of cosmic risk. It is not binary, with no concept of safe or doomed. This is a probabilistic, uncertain process filled with surprises. Our detection system, a network of telescopes and observations we rely on for alerts, is not designed to handle such surprises. It is designed to work with predictable objects on stable orbits. When something unpredictable happens, when the object is hidden in bright light or suddenly becomes brighter or sheds fragments, the system fails, and we have to confront this problem. Now we will delve into the question. We will examine past approaches of asteroids that pass by Earth with little warning, as well as detection failures that no one wants to discuss. Part 6. Examples. Asteroids that we detected only days or minutes before their flyby. In early 2025, an asteroid designated 2025 TF passed within about 400 kilometers of the Earth's surface. 400 kilometers. That's closer than the International Space Station. That's closer than most satellites. It is below the orbital level of many spacecraft. We didn't notice it until it was almost next to us. 2025 TF is small, probably only a few meters in diameter. At that size, even if it entered the atmosphere, it would have burned up, creating a bright fireball without harming the Earth. The Chelyabinsk meteor in 2013 had a diameter of about 17 to 20 meters and exploded in the air with a force of several hundred kilotons of TNT. He shattered windows, injured over 1,000 people, but left no crater. 2025 TF was smaller. It would have been just a light show and nothing more. But the essence is not in the size. The main thing is the delay in detection. We didn't notice it until it was almost above us. He flew over Antarctica, one of the most remote corners of the Earth, where very few people watch the sky. If he had come a few hours earlier or later, if his trajectory had changed slightly, he might have flown over a populated area, and we would not have received a warning. This is not an isolated case. In recent years, several small asteroids have been detected only days, hours, or even minutes before their closest approach. Some were noticed only after they had passed by. They flew past Earth, remaining invisible to our observations, and we only noticed them on the exit. This is due to the limitations of our detection system. Telescopes have minimum brightness thresholds. Small objects glow faintly. If they approach from the direction of the sun, they are impossible to see. If they move at high speed, they cross the sky too quickly for automatic systems to detect them. If the objects are dark with low albedo, they reflect very little sunlight and blend into the background. The problem of detection is not just theoretical. It is a practical, observable issue. We miss objects. We often overlook them and usually learn about a missed object only when someone accidentally looks at the right part of the sky at the right time and notices something moving. The consequences could be more serious than you think. Yes, most small asteroids burn up harmlessly, but not all. And even a small object, if it hits the right target, can cause catastrophic damage. A few meters of stone colliding with a satellite at orbital speed will destroy it instantly. A collision with the International Space Station would be fatal. A strike on a city, even from a small object, can destroy buildings and kill thousands of people. The atmosphere serves as a shield, but it is not an ideal shield. Objects larger than 20 meters can reach the Earth's surface. Smaller objects can still cause destructive air explosions, and there is also the problem of debris. When an asteroid disintegrates in the atmosphere, it scatters fragments over a large area. Most fragments are small, but some can be large enough to cause harm. If the disintegration occurs over a densely populated area, these fragments become projectiles. An event in Chelyabinsk scattered meteorites over hundreds of square kilometers. People collected them as souvenirs, but if the object had been larger or the explosion occurred at a lower altitude, the fragments would have been more dangerous. Now let's scale this situation. Instead of one small asteroid, imagine a cloud of debris from a disintegrating comet. Instead of a few meters of rock, envision hundreds or thousands of pieces, from dust to boulders, scattered across the orbit. Instead of a single point of impact, imagine a diffuse threat, a statistical risk, where the likelihood of one specific fragment hitting is low, but the cumulative probability is not negligible. This is what happens when comets break apart. They don't create one projectile. They create a shotgun effect. The R2 comet has a tail measuring 7 million kilometers, the distance between Earth's orbit and the comet. If the comet breaks apart, fragments may scatter along the orbit, some getting closer, not to zero, not to a collision, but nearer. Close enough for the statistical probability to shift from negligible to small, but not zero. A small yet non-zero probability is enough to raise concerns among risk analysts. This is a lesson from the case of Object 2025 TF and similar ones. The delay in detection is real. We do not see everything. We do not see most objects if they are small or fast or come from the wrong direction. The asteroids we catch follow established rules. They appear on predictable trajectories, coming from specific directions at the appointed time. Those who ignore these rules instill fear in us. They are the ones we let slip away. Next, we will talk about how comets can be dangerous, even without colliding with us, as their debris and dust trails create threats that linger long after the main object has left this place. Part 7. Fragmentation of comets and the dangers of dust trails. Realistic speculative scenarios. Even if a comet passes by, its debris can cause harm. Let me explain how this happens. Comets are not solid rocks. These are loose aggregates of ice, dust, stone, and organic compounds held together by weak gravity and surface tension. They become fragile as they approach the sun. Thermal stress causes them to crack. The release of gases creates pressure that tears them apart. Under tidal forces, if they approach a massive body, they can be torn apart. Sometimes they disintegrate quietly, losing small fragments. Other times, they explode with a loud noise, breaking into dozens of shards. Comet Shoemaker-Levy 9 is a well-known example. In 1992, it got too close to Jupiter and was torn apart by tidal forces. More than 20 fragments spread along its orbit. 2 years later, they collided with Jupiter one after another, causing powerful explosions visible from Earth. Each impact released energy equivalent to millions of nuclear bombs. The scars in Jupiter's atmosphere lingered for months. It was spectacular. It also demonstrated how fragile comets can be and how dangerous their debris is. Another example is Comet 73, Lashvasman-Bachmann. It fragmented several times. In 1995, it broke apart into several pieces. In 2006, it shattered again, this time into dozens of small fragments. Observers watched in real time as the comet disintegrated, each fragment developing its own tail and trajectory. Over time, they formed a stream of debris, a river of ice and dust, moving along its original orbit. The Earth passed through parts of this stream, resulting in a temporary increase in meteor activity. Nothing catastrophic, but noticeable. Now apply this to Comet R2, which has already shown activity at least once, indicating internal instability. If it breaks apart, the pieces will scatter. The rate of dispersion depends on the relative speeds, which depend on the energy of the fragmentation event. Gentle separation leads to slow divergence, while a strong explosion causes rapid separation. In any case, over time, fragments drift apart, and the same happens with the dust they produce. Dust is a real threat. Each comet continuously releases dust as it sublimates. Dust particles, tiny from microns to millimeters in size, move at speeds of tens of kilometers per second. At such speeds, even a grain of sand carries immense kinetic energy. If a dust particle collides with a spacecraft, it can penetrate the hull. If she damages the satellite, it could lead to the failure of solar panels, sensors, or communication equipment. If a particle hits a person during a spacewalk, it could have fatal consequences. For example, the International Space Station is protected from micrometeoroids. The station's shields are multi-layered and designed to evaporate incoming particles before they can breach the hull. But these shields are not perfect. Large particles or those arriving at unusual angles can penetrate the protection. The International Space Station has already endured impacts several times. Most of them cause minor damage, but some cases required repairs. A dense stream of meteoroids formed during the comet's breakup significantly increases the risk. Now let's consider the geometry. The minimum distance from the comet's orbit to Earth's orbit is 7 million kilometers. If the comet breaks apart and its fragments start to spread along the orbit, some of them may come closer to Earth's path. Not too close, but closer. And if the Earth passes through a stream of debris at an inopportune time, we may encounter an increased concentration of particles. This could lead to intensified meteor showers, damage to satellites, or micrometeoroid impacts on spacecraft. The probability that a single particle will hit a specific target is low. The cosmos is vast, and the targets are small, but the cumulative probability that something somewhere will be damaged is higher. In our days, there are many objects in orbit, thousands of satellites, space stations, manned spacecraft, all potential targets. There is also a scenario of interaction with the atmosphere. If the Earth passes through a dense stream of dust, even if the particles are small, the cumulative effect can be noticeable. The brightness of the high-flying atmosphere may increase, and the activity of light phenomena may rise. Bright meteors exploding in the upper layers of the atmosphere may become more frequent. Astronomy enthusiasts will notice it, and meteor cameras will capture the anomaly. It won't be a catastrophic event, but it will be unusual. Unusual phenomena typically cause anxiety. The real problem lies not in the dust we see, but in the debris that goes unnoticed. A piece the size of a boulder, 1 to 2 meters in diameter, moving at 30 kilometers per second, will be nearly invisible until it is too late. Optical observations can capture it, but only if directed at the right part of the sky at the right moment. If the fragment approaches from the direction of the sun, it will be invisible. If it is dark with low albedo, it will be nearly impossible to detect. And if it enters the atmosphere over a populated area, the consequences could be comparable to the event in Chelyabinsk or even worse. Assessing the probability in this case is difficult. We do not know if the comet has broken apart, if it will break apart, how many fragments may form, or how they may spread. We do not know the distribution of sizes, speeds, or trajectories. We have only the orbit of the parent comet and a gap of 7 million kilometers between this orbit and the trajectory of the Earth. Within these parameters, one could say that the probability of a fragment colliding with Earth is low, but a low probability is not equal to zero. And when the consequences of a mistake are measured in human lives and infrastructure, not significant is not always small enough. Visualization helps again. Imagine the orbit of a comet as a thread in space. Now imagine that this thread unravels, splitting into dozens or hundreds of thinner threads, each slightly different. Some threads remain close to the original path, while others deviate. Over time, the cloud of threads spreads, forming a blurred canvas along the orbit. The Earth's orbit is another thread crossing the fabric at an angle. Most of the time, Earth moves through empty space, but sometimes it intersects the fabric, and at that moment, particles fall to Earth. This is not unprecedented speculation. Meteor showers are exactly this phenomenon. Perseids, Leonids, Orionids all represent streams of comet debris. Every year, Earth passes through these streams, and we observe meteors. Usually harmless, sometimes spectacular, and very rarely dangerous. In the year 1833, the Leonid meteor storm produced tens of thousands of meteors per hour. Witnesses describe a sky filled with fire. If it happened today, with our satellite infrastructure, the damage would be significant. R2 is not predicted as a source of the meteor storm. Its remnants, if they exist, are probably too sparse. But we do not know this. We cannot know until we see, and by then it may be too late to take any action other than to observe. Now we will pose a more global question. Are we observing the growth of unexpectedly appearing objects, or is it just an observational bias? Is the solar system sending us more objects, or have we finally started to notice them? Part 8. Pattern recognition. Let me list them. Oumuamua arrived in October 2017. It was the first confirmed interstellar object detected in our solar system. It was strange, elongated, rotating, accelerating in a way that did not match our models. He left our system before we could study him properly. Then in August 2019, Borisov appeared. The second interstellar visitor, which was clearly a comet with a coma and tail, and its composition matched what we expect from debris of another star. Now we have 3 Atlas AIs open in the year 2025, another interstellar object. It's either an asteroid or a comet core, depending on whom you ask. It changes color. It's strange. And while the world observes the 3 objects Atlas, R2 stealthily penetrates our solar system, remaining unnoticed until perihelion. 4 objects in 8 years. Oumuamua, Borisov, 3 objects Atlas, R2, different sources, different compositions, different circumstances of discovery, but all unexpected. They all appeared with little or no warning. Is this a pattern? Is this growth? Or is it just what happens when you finally start paying attention? There are 3 hypotheses. The first is observational bias. We now have better tools. More telescopes, more studied skies, large-scale research, more amateur astronomers with access to professional data. We look closer, so we find more. Observation systems like Pan-STARRS, ATLAS, and the upcoming Vera Rubin Observatory are designed to capture transient events, moving objects, everything that changes. As these systems begin to operate and improve, the detection level increases. This does not mean that there are more new objects. It means that we finally see objects that have always been nearby. The second hypothesis suggests a real increase in the dynamic flow. Perhaps something is disrupting the Oort cloud. Perhaps a passing star, long gone, sent a wave of comets inward, and we are now seeing the first arrivals. Perhaps our solar system is moving through an area of space with a higher density of debris. Perhaps galactic tides, the gravitational influence of the Milky Way structure, are pushing more comets into the inner system. This is not excluded. The Oort cloud is enormous and contains trillions of comets. A slight disturbance could send thousands of them inward over a few thousand years. From our perspective, trapped in short human timeframes, It would appear as a sudden surge. The third hypothesis, statistical clustering, pure randomness. Random processes create clusters. Flip a coin 100 times, and you'll see a sequence of heads or tails. This does not mean that the coin is unevenly balanced. It means that randomness is clustered. 4 unexpected visitors in 8 years may just be noise, a statistical fluctuation without deep meaning. After 8 years, we may see none, or conversely, 10. Without additional data, we cannot separate the signal from the noise. Each hypothesis has its evidence. The observational bias is strong. The number of known asteroids close to Earth has exploded in the last 2 decades, not because asteroids suddenly appeared, but because we began systematically searching for them. The same is likely true for comets. Swan discovered thousands of comets, most of which are solar seekers, simply because Swan can see what optical telescopes cannot. As our detection network expands, so does the catalog. But observational bias does not explain everything. Oumuamua was indeed strange. Its elongated shape, unobservable acceleration, and lack of a visible coma all defied simple explanation. Some astronomers suggested that this is a fragment of a planet torn apart by tidal forces in another star system. Others hypothesized about a hydrogen iceberg, a nitrogen iceberg, or a shard of frozen gas. The suggestions became increasingly exotic, as simple explanations were inadequate, and then he left, and we lost the chance to study him further. The 3 eyes of the atlas are also strange. Its color changed from red to green, or so it seemed, depending on which observations you trust. Asteroids usually do not behave this way. Color arises from surface composition. A color change indicates a change in composition, suggesting that the surface is not uniform. Perhaps it spins, and different sides reflect different wavelengths. Maybe it slightly evaporates, altering the observed spectrum. Perhaps the reason lies elsewhere. We do not know because we have not approached closely enough to find out. Object R2 fits into this picture differently. It is not interstellar. It originates from the solar system, likely from the Oort cloud, but it hid in the sunlight and only appeared after perihelion, demonstrating how easily we can overlook something even in our own backyard. If R2 can hide, then other objects can too. How many long-period comets pass through the inner part of the solar system unnoticed each year? We don't know. We only see those that are bright enough, that remain visible for a long time, that cross our thresholds of detection. The others are ghosts. Is there some pattern? Perhaps. An optimistic interpretation is that we become better at seeing the universe as it is, full of temporal visitors, streams of debris, and unexpected arrivals. A pessimistic interpretation claims that the speed of object emergence is increasing, and we are unprepared for it. A realistic interpretation likely lies somewhere between these two views. We see more because we look closer, but we also discover that the base speed of space traffic is higher than we thought. The solar system is not a quiet neighborhood, but a highway, and we are just beginning to set up surveillance cameras. In the next part, we will examine the institutions that manage this traffic, data channels, bottlenecks, and the silence that breeds distrust. Part 9. Institutions, Silence, and the Life Cycle of Information. Let me explain how discovery becomes public knowledge. An observer, whether a professional or an amateur, notices something unusual. A moving object, a bright source, a transient event. They record the position, time, and size, checking if it is already known, and if not, they report it. Where do they report it? At the Center for Small Planets, managed by the International Astronomical Union, serving as a hub for observing asteroids, comets, and other small celestial bodies. He gathers data from observers around the world, verifies it, and issues bulletins when something new is confirmed. However, verification takes time. One observation is not enough. Several observations are needed to confirm that the object is real, eliminate instrumental artifacts, and calculate a preliminary orbit. This means waiting for other observers to aim at the same section of the sky and confirm the observation. If the object is weak, if it is close to the detection limit, if it is moving fast, confirmation can take days, sometimes longer. Once the object is confirmed, the Minor Planet Center assigns it a preliminary designation and publishes an electronic circular. Data becomes public, accessible to all, but these are raw data, orbital elements, position vectors, magnitude estimates. This is not a press release or a headline. It is a technical document for astronomers. The general public does not read MPC circulars. They read news articles, which appear later, if they appear at all. Meanwhile, other institutions clarify the orbit. The Jet Propulsion Laboratory manages the Horizon System, which calculates the precise trajectories of solar system objects. As new observations come in, the orbit solution improves, uncertainties decrease, and predictions become more reliable. If the object is potentially hazardous and its orbit brings it closer to Earth, JPL marks it. The Center for Near-Earth Object Studies, CNEOS, assesses the risk. If the risk is high enough, NASA issues a statement. If the risk is low, it may not happen. As for R2, the process looked like this. Vladimir Bazugli, an astronomy enthusiast, noticed an object in SWAN data on September 11, 2025. He reported it. Other observers confirmed his optical observations. MPC issued a circular designating it C/2025 R2. JPL calculated the orbit, and CNEOS conducted an assessment. The conclusion was, there is no threat. The closest approach will be 0.26 astronomical units, far enough for safety. No press release, no public warnings, just a technical update buried in the database. And here, silence begins. Not because someone is hiding something and not due to a conspiracy, but because the system is designed to reduce risks, not to interact with the public. If an object is not a threat, it doesn't make the headlines. And if it doesn't make the headlines, most people will never hear about it. R2 was mentioned in several astronomical publications and on some space websites. It made it into the astronomy picture of the 18th of September. But he did not become a trend on social media and did not dominate the news cycle. He was just another comet, one of dozens discovered each year. In contrast, the 3I Atlas, interstellar, mysterious, color-changing, with unusual acceleration, is headline material, a story that makes it into the main media narrative and is discussed in comments. It doesn't matter that the 3I Atlas is harmless, that its closest approach is 1.8 of an astronomical unit, that it poses no risk. What matters is that it is interesting. Interesting things attract attention, creating a vacuum when institutions do not provide detailed and accessible updates, when the information cycle is slow and technical, and when the gap between discovery and public awareness stretches for weeks or months. Speculation fills this space. Social media users notice gaps, ask questions. Why aren't we hearing more about this? Why is the coverage so modest? Is something being hidden? In the absence of official answers, unofficial versions emerge. Theories, conspiracies, rumors. The discovery of R2 by Vladimir Bazugli is particularly notable. He is not a professional astronomer, nor does he work for a space agency. He is an amateur who knows how to analyze SWAN data. The fact that he discovered the comet before professional observational programs is not a failure of the specialists. This reminds us that the detection network is not perfect, that unconventional approaches matter, and sometimes the most important observations come from unexpected sources. But it also raises questions. If an amateur can find a comet missed by professional astronomers, what else are we overlooking? How many objects pass through the inner solar system unnoticed because they are in the wrong place at the wrong time? Due to observations being conducted in another direction, because of the bright sky or bad weather, or because the instrument is under repair, we do not know, cannot know, and that is the problem. The cycle of information is slow by design. Verification prevents false alarms, caution prevents panic, but caution also creates gaps, and gaps breed doubt. When people stop trusting the institutions that are supposed to tell them the truth, they seek alternative sources, which are not always reliable. Next, we will analyze wild ideas, conspiracy claims, and theories on the edge of science. We will separate what is worth considering from what is not. Part 10. Curiosities and Conspiracies. Allow me to clarify. Some will claim that object R2 is not natural. They will say that it is a probe, a device, or artificial apparatus sent by someone or something to observe us. They will claim that the trajectory is too convenient, the timing too perfect, and the surge of activity too controlled. They will claim that NASA knows more than it says, that images are hidden, and that the real data is classified. They will consider this a message, a warning, or a test, and they will believe in it. So, let's analyze these statements in order and see which ones truly deserve attention. The first statement, R2 is an artificial object. Is this physically possible? In principle, any sufficiently advanced civilization could create a spacecraft mimicking a comet, covering it in ice to simulate comet behavior when heated, programming it for bursts of activity on a schedule, and designing a trajectory that passes close to Earth. It is possible, but not simple, and such a creation leaves traces. If R2 were artificial, we would expect anomalies. Spectroscopy would show unusual compositions, elements, or molecules not corresponding to the natural chemistry of comets. The core would have structures, geometric shapes, and regularities absent in natural objects. The trajectory would show fine-tuning, small adjustments incompatible with gas emissions, as well as electromagnetic radiation, radio signals, infrared signatures, something indicating active systems. We observed nothing like it. The spectrum looks like that of an ordinary comet. The coma aligns with sublimating ice, and the trajectory follows the laws of gravity. There is no signal. Occam's razor states that the simplest explanation is usually correct. R2 looks like a comet because it is a comet. Attracting artificial sources requires adding assumptions, complications, and introducing participants with unknown motives and capabilities. This is possible, but not necessary, and in science, we do not resort to unnecessary explanations. Statement 2. Images are suppressed. Do we see everything? Almost certainly not. Professional observatories do not publish every image they receive. They process data, calibrate, filter noise, and select the best frames. Some data is confidential, intended for research groups that proposed the observations. Some data is of low quality and not worth publishing, but suppression implies intent and coordinated efforts to conceal information, requiring a level of coordination that is hard to achieve. Observatories are scattered around the world, working independently, and astronomy enthusiasts have their own equipment. If something dramatic were visible, someone would have published it. The fact that we do not see dramatic images indicates that they do not exist, not that someone is hiding them. Assertion 3. The trajectory is manipulated. Can an external force control comet R2? If you mean aliens, then we return to the first assertion. When it comes to natural forces, yes, gas emissions create no gravitational accelerations. Comets are not ballistic objects, they control themselves by emitting gas. R2 is in a state of outburst, meaning it is emitting gas, which affects its trajectory. JPL models account for non-gravitational forces and gas outbursts. The trajectory forecasts are not perfect, but accurate enough. If the comet were under active control, we would observe deviations from the models that could not be explained by gas outbursts, but this did not happen. Statement 4. Statement. It is harmless, but symbolic. Some claim that even if R2 is safe, even if it doesn't collide with us, its appearance matters. It's a sign, an omen, synchronicity. This is not a scientific statement, but a philosophical or spiritual one. Science can tell about the orbit, composition, and probability of collision, but it cannot say whether the universe is sending you a message. This goes beyond empirical study. If you find meaning in the appearance of a comet, that is your choice. But do not confuse personal meaning with physical risk. Now, are there any statements that deserve closer examination? Yes. 1. The possibility of fragmentation and the dangers from debris are real. This is not a conspiracy. It is physics. If R2 fragments, if it sheds pieces deviating from its native trajectory, these pieces could pose a danger, likely not a collision threat, but a danger from debris, a stream of micrometeoroids, a threat to satellites. This needs to be monitored and prepared for. It's speculative, but based on what we know about comet behavior. The prioritization matrix looks as follows: artificial origin, impossible without evidence; suppression of the image, unlikely considering the distributed nature of observations; manipulation of the trajectory, no evidence except for natural gas; symbolic meaning, unscientific; fragmentation of debris, likely unworth tracking. Speculation is fascinating. It is human nature to see patterns, imagine agents, and fill gaps with stories, but we must always be ready to check these stories against data. And when the data does not support the story, we must have the discipline to reject it and move on. Now we will shift our attention to other recent scientific headlines, starting with neurobiology, because the brain is also a detection system and it has blind spots. Part 11. Neurobiology. The University of California, San Francisco, has discovered a protein that slows brain aging. In August 2025, researchers from the University of California, San Francisco, published results about a protein that seems to regulate brain aging. The protein, identified in experiments with elderly mice, appears to act as a brake on neural plasticity. When the researchers blocked this protein, elderly mice showed improvements in memory and learning. Their neurons worked more reliably, and their synaptic connections strengthened. In some measures, their brains behaved like those of younger individuals. The experiment was quite simple. They took old mice, identified the protein that accumulates with age, blocked its activity using medication or genetic manipulation, and then tested whether behavior would improve, with promising results. Elderly mice, having received treatment, performed better on memory tasks, navigating mazes faster, and recognizing objects more reliably, the effect being measurable, reproducible, and statistically significant. But this is work with mice. Their brains are simpler, smaller, and organized differently than humans. What works on mice does not always apply to humans. The history of neurobiology is full of methods that cured mice but failed in clinical trials. Alzheimer's disease has been cured in mice dozens of times, yet humans are still waiting, so caution is necessary. The results are exciting but preliminary, and the consequences, if confirmed, are huge. Cognitive decline is one of the most frightening aspects of aging. Memory loss, learning difficulties, slowed perception, all of which threaten independence and identity. If blocking a certain protein can slow down or reverse this decline, the consequences will be significant not only for individuals, but also for societies facing aging population issues. The economic costs of dementia are measured in trillions of dollars worldwide. Treatments that delay the onset of the disease by even a few years can save enormous resources and reduce suffering. But there are complications. Proteins do not act in isolation. They are part of networks, cascades, feedback loops, and blocking one protein can have consequences and disrupt other systems. Old mice in the study showed no obvious side effects, but the observation period was short, and long-term consequences are unknown. Humans are more complex. We live longer, accumulate more damage, and have more comorbidities. Treatment that is effective on mice may interact unpredictably with human biology. Here is a metaphor. The brain is a detection system, scanning the environment, processing signals, forming memories, making predictions. When he works well, he captures details, adapts, learns. With age, he loses sensitivity. Signals become weaker, noise appears, and patterns are harder to distinguish. A protein identified by researchers from the University of California, San Francisco, seems to participate in this degradation process. By blocking it, scientists restore some youthful brain sensitivity. Now think about our astronomical detection systems. Telescopes scan the sky, process signals, catalog objects, and predict trajectories. When they work effectively, they capture faint comets, track asteroids, and warn of dangers. But even these systems degrade. Tools become outdated, sensors lose accuracy, calibration becomes less precise, and data streams fill with noise, and over time we start to miss what we once noticed. The parallel is not perfect, but it is instructive. Both systems, brains and telescopes, are designed to detect patterns in noisy environments. Both degrade over time, and both can be partially restored through intervention. For the brain, it may be a protein blocker. For telescopes, recalibration, sensor replacement, or algorithm updates. The principle is simple. Vigilance requires maintenance. The UCSF study reminds us that hidden mechanisms control what we see and what we miss. Sometimes the mechanism is biological, like a protein that accumulates with age. Sometimes it is technological, when the sensor loses alignment. Sometimes it is an institutional factor, like a survey schedule that leaves gaps. The solution is always the same. Identify the mechanism, understand how it works, and then intervene to restore function. In the next section, we will examine another news story from the field of neurobiology, this time about Alzheimer's disease, as it is important to understand the pattern of sensational claims and cautious realities. In October 2025, a new wave of headlines emerged. Alzheimer's disease was reversed in mice. Articles were full of excitement, and social media posts were hopeful. However, reality turned out to be more complicated. Researchers tested a new intervention, possibly restoring vessels, perhaps cleansing amyloids or regulating proteins. Details varied depending on the study you read, but the theme remained unchanged. Elderly mice with cognitive impairments showed improvement after treatment. Their brains cleared of plaques and memory improved. In some cases, the pathology was reversed. This is not the first case. Research on Alzheimer's disease over the past 2 decades has yielded many promising results in mice. Vaccines that eliminate amyloid, drugs that reduce tau chains, gene therapies that restore synaptic function. These methods work in mice. Most people are ineffective. The problem of translation is immense. Alzheimer's disease models in mice do not fully reflect human pathology. Mice do not live long enough to develop the full spectrum of the disease. Their brains are simpler, the immune system is different, and metabolism is faster. A treatment that shows results in a 6-month study on mice may fail in a 10-year trial on humans. Sample size matters. Mouse studies often involve dozens of animals, while clinical trials require thousands of participants. Time is of the essence. Mouse experiments last for months, while clinical trials take years. Side effects are important. A treatment safe for mice may be toxic to humans. Effectiveness matters. A treatment that improves memory by 20% in mice may only improve it by 5% in humans, and those 5% may not have clinical significance. The summary in Newsweek, like many popular science articles, emphasizes the positives. Reversal, breakthrough, hope. These words attract attention. However, the original sources, meaning the actual scientific studies, are more cautious. They use words like preliminary data, limited results, further research required. They acknowledge the complexities of translation and do not claim victory, but speak of progress. This is the problem. Complex science becomes sensational headlines. Nuances are lost. Uncertainty fades. The gap between what researchers actually discovered and what the public believes only widens. And when the treatment ultimately proves ineffective for people, when the results of the clinical trial are negative, the public feels deceived. They were promised healing, but received yet another disappointment. Trust your own path. This scheme is not unique to Alzheimer's research. It is observed in every field where the stakes are high and the science is complex. Cancer research, climatology, infectious diseases, and yes, astronomy. When a new comet appears, headlines speak of spectacular phenomena, unique events visible to the naked eye. In reality, it turns out to be much less impressive, more uncertain, and dependent on variables we cannot control. Comets fade, break apart, and disappoint. The public, awaiting a spectacle, feels let down. The lesson is to show skepticism, not cynicism. Skepticism. When you see a headline claiming a breakthrough, read the original source. Check the sample size. Look for caveats. Ask what exactly the researchers measured and what conclusions they drew. Learn about the limitations. Ask what will happen next. Most often the answer will be, more research is needed. And that's okay. That's the nature of science. But that's not how headlines work. Headlines need certainty. Science operates on probabilities. The parallel with the comet is as follows. The comet is real. Observations are real. Orbital calculations are real. But forecasts, predictions of brightness, decay scenarios, these are all probabilities. We do not know what will happen. We know what might happen, and the likelihood of these events varies. Responsible behavior involves clearly presenting these probabilities without exaggerating or downplaying them, avoiding clickbait. Next, we turn to artificial intelligence, another area where hype and reality diverge, but also a field where real possibilities change our approach to detecting cosmic threats. In October 2025, several significant events occurred in the field of artificial intelligence, with new models, tools, and capabilities being introduced, expanding the boundaries of machine learning. Fundamental models with improved logical reasoning, better context management, and faster data processing. Companies and research laboratories have introduced systems capable of processing longer contexts, maintaining coherence in complex reasoning chains, generating code more reliably, and interacting with multiple modalities simultaneously. The pace of development is steady. What seemed impossible 2 years ago has now become routine. What looks like routine today will be outdated in 2 years. The acceleration is real, measurable, and shows no signs of slowing down. Considering technological progress and ethical initiatives aimed at aligning the development of artificial intelligence with human values, global forums supported by researchers and politicians have been launched. Details may vary, but the theme remains unchanged. Artificial intelligence is powerful, it is accelerating, and we must ensure it aligns with what we truly want, not just what we think we want, but what we genuinely value when the consequences become real. The question is not only what artificial intelligence can do, but also what it should do and who makes the decisions. These are not abstract philosophical questions. They are urgent, practical problems. As artificial intelligence systems become increasingly capable, autonomous, and integrated into critical infrastructure, the stakes rise. A mistake in medical diagnosis can lead to death. An error in traffic management can cause accidents. An error in astronomical detection can leave us blind to impending threats. Artificial intelligence is already integrated into data streams in astronomy. This is not speculation. It is current practice. Automated anomaly detection scans images to identify transit events. Machine learning algorithms classify objects, distinguishing between asteroids and stars, comets and galaxies, supernovae, and variable stars. The classification occurs in milliseconds. It would take a human minutes or hours to do the same work. Algorithms refine orbits by taking sets of position measurements and calculating trajectories. They predict future positions, assess uncertainties, and mark objects whose orbits bring them closer to Earth. They identify potential threats, objects that may pose collision risks, which may require additional observation, and could be added to monitoring lists. The volume of data is too large for humans to process manually. Modern wide-format studies generate terabytes of data overnight. Each image contains millions of sources. Each source must be measured, cataloged, and matched with existing databases. Temporal events are things that appear, disappear, or change their brightness, and must be identified and marked. The Vera Rubin Observatory, when fully operational, will image the entire visible sky every few nights. It will be able to detect billions of objects. Tens of thousands of them will move, change, and pass as temporary phenomena. No human team can process such a volume of information. We need artificial intelligence to filter out the excess and find signals hidden in the noise. Without AI, modern astronomy will drown in its own success, overwhelmed by the vast amount of information coming from telescopes every night. But artificial intelligence is not infallible. It can make mistakes. He marks false alarms, objects that appear dangerous but are not. A cosmic ray hits the detector, leaving a bright streak. The artificial intelligence perceives it as a fast-moving object and labels it as a potential asteroid. Subsequent observations reveal nothing. The object never existed. It was an artifact, a glitch, a phantom, or an AI classification error. A distant supernova gradually brightens. The light curve resembles that of a variable star. The artificial intelligence misclassifies it. Days pass before a person notices the mistake and changes the classification. By this time, the optimal window for observations has already closed. Important data has been missed. Artificial intelligence overlooks real signals, especially if they are unusual or do not match the training data. Machine learning systems learn from examples. You show the system thousands of asteroids, and it understands what they look like. You show it thousands of comets, and it recognizes their shape. But what happens when something appears that doesn't resemble the training examples? What happens when an object has properties that go beyond the distribution on which the AI was trained? The system may label it as noise, an artifact, or something to be ignored. Either she may mistakenly classify him, assigning him to the wrong category, which will lead to his incorrect processing. In any case, the signal will be lost, and this may amplify biases. If the training dataset is biased towards certain types of objects, then artificial intelligence will also be biased. Suppose that most of the training data consists of objects observed through optical surveys in certain parts of the sky. At certain times of the year, under specific observational conditions, the AI learns this pattern. It understands that asteroids usually have certain brightness ranges, specific colors, and certain speeds. Then an object appears that deviates from this pattern. Perhaps it is darker than usual with a lower albedo, reflecting less sunlight. Perhaps it moves faster or slower than expected. Perhaps it came from an unusual direction. An artificial intelligence trained on biased data does not recognize it. It will filter it out. He will catch what he was trained to catch and miss everything else. There is also the problem of noise abundance. The better the AI recognizes anomalies, the more alerts it generates. This seems like a positive aspect. More detections mean better coverage and fewer missed objects. However, a greater number of signals means more subsequent observations, and more subsequent observations require more time on the telescope, more human effort, and more resources. Telescopes are expensive. Time at a large observatory costs thousands of dollars per hour. It's impossible to track every signal. Priorities must be set. Decisions need to be made about which objects are worth the investment and which are not. If the false alarm rate is high, the system becomes overloaded. Astronomers spend all their time chasing ghosts and miss real threats. Finding a balance between sensitivity and specificity is a complex task. Sensitivity is the ability to detect real signals. Specificity is the ability to reject false signals. Both indicators must be high, but in practice, compromises have to be made. Increasing sensitivity captures more real objects, but also more false alarms. Increasing specificity discards more false signals, but also misses more real objects. The ideal zone where we can catch most real threats without causing too many false alarms is narrow and constantly changing. It depends on the quality of data, observation conditions, and the characteristics of the sought objects. This requires constant adjustment, ongoing feedback, and human oversight. Let's imagine a hypothetical situation. An artificial intelligence analyzing data about the brightness of a comet detects a strange spike in the light curve P2. The comet gradually brightens since its discovery, corresponding to the increase in solar heating as it approaches the star. Then, on October 15th, the brightness sharply increases, not by much, perhaps half a magnitude, but the jump is sharp, sudden, and does not match the smooth changes predicted by the models. It looks like a spike, but the timing is strange. The pattern does not align with previous spikes. They occurred near perihelion, when solar heating was at its maximum. This same spike is observed weeks later, as the comet moves away from the sun. Is this unusual? Is it a tool artifact? Could the telescope have made a tracking error? Perhaps the atmospheric conditions have changed, or maybe the calibration was incorrect. Or is it something unexpected, something physical happening with the comet? A fragment ejection, a collision with a meteoroid, a sudden release, an expulsion of volatile substances. The artificial intelligence cannot determine this. He does not understand physics. He has no models for comet behavior. He simply compares data with templates he has seen before. This template is unusual, so he marks the anomaly and relays it to a human. The human astronomer receives the signal. It is one of dozens of messages in a day. She looks at the data, sees a spike, checks other tools. Has anyone else observed R2 recently? Are there independent measurements confirming the brightness change? She searches databases but finds nothing. The spike appears only in one dataset. This raises suspicions. Artifacts typically occur in only one dataset. Real events are usually recorded in multiple datasets, unless the timing was unfortunate and only one telescope was looking at the right moment. She checks the observation log. Were there any issues that night with a telescope, detector, and weather? The journal records scattered clouds, variable visibility, nothing unusual. She reviews images before and after the outburst. The comet looks normal, no obvious structural changes, no new fragments. There was no dramatic bright glow in the subsequent observations. The surge seemed to be temporary, if it even occurred at all. It might have been noise. Perhaps it was real, but brief, lasting only a few minutes, insufficient for confirmation by other observers. She makes a decision. The evidence is ambiguous. The burst could have been real, but it is likely an artifact. Without confirmation, issuing a warning would be premature. This would require resources, trigger subsequent observations, mobilize other astronomers, and if the spike turns out to be nothing, it would waste everyone's time. She decides not to issue a warning. The anomaly is recorded in the database as unconfirmed and forgotten. She moves on to the next warning. The system continues to operate, but what if it was really something important? What if the spike indicates fragmentation and pieces are now diverging from the parent trajectory? A human decision made in uncertainty with incomplete data might have overlooked something important. Fragments take time to separate. In the first hours or days, they are close to their parent. They are difficult to distinguish even with high resolution. By the time they are far enough away to be seen as separate objects, they may spread out to represent individual threats, while the AI that detected the anomaly is ignored, not due to human negligence, but because she followed protocol. She evaluated the evidence. She made a reasonable conclusion, but rational decisions made in uncertainty can sometimes be wrong. Over time, people begin to distrust AI warnings because most of them are false alarms. This phenomenon is well documented in medical diagnostics, aviation safety, nuclear power plant operations, and now in astronomy. When alarms sound too often and without consequences, people stop responding with the necessary urgency. They begin to ignore them. They are developing heuristics for filtering noise. Perhaps I will only respond to alerts with confidence levels above 90%. Perhaps I will act only if several devices mark the same object. Perhaps I will lower the priority of warnings from old telescopes with known calibration issues. These heuristics are rational. They save time. They focus resources on the most promising objects, but sometimes these heuristics also filter out the signal. A real threat, the one that truly matters, can have an 85% confidence level. It may be detected by only one device, as only one was aimed at the target at the right time. It may come from an old telescope that, despite its age, still captured something real. And when this warning arrives, it is dismissed as noise. The pattern recognition that helps people cope with information overload also blinds them to true anomalies. This is the challenge of cooperation between humans and artificial intelligence. Neither is perfect. AI is fast, but not wise. He processes vast amounts of data in seconds, identifying patterns that would take a human hours, never tiring or losing focus. But he lacks understanding of context. He has no intuition. He cannot reason whether an anomaly has physical meaning. People are slow but intelligent. They understand physics. They have intuition. They can reason about cause and effect and plausibility. However, they are limited by attention, fatigue, and cognitive biases. They can only consider a small part of the data. They overlook things happening outside their focus. The system works best when both sides complement each other, when artificial intelligence processes the volume and a human makes decisions. Artificial intelligence scans all information, marks something unusual, and transmits it to people for evaluation. People study the marked elements, applying context and intuition to determine what is real and what is noise. But this requires trust, calibration, and feedback. People must trust that artificial intelligence will not miss critical signals. AI must be calibrated so that its notifications are informative rather than overwhelming. There must be feedback mechanisms allowing people to inform artificial intelligence when it is wrong or right. Only then can the system learn and improve. It is also necessary for people to remain vigilant. They must not become complacent and assume that artificial intelligence catches everything. The moment people start to think of artificial intelligence as an all-knowing tool that never makes mistakes, the system becomes dangerous. Because artificial intelligence is not infallible. It is a powerful but limited tool that requires human oversight to function correctly. The danger lies not in the possibility of artificial intelligence failing. The danger is that people may trust him too much and stop paying attention. And when they stop paying attention, the number of missed moments increases. Detection no longer depends solely on the hardware. It's not just about creating large telescopes with better mirrors and more sensitive detectors. It's software, algorithms, decision trees, neural networks, and statistical thresholds. These are the rules we create to distinguish signal from noise, the models we build to predict trajectories, the pipelines we create to process data. And all this is created by people trained on data chosen by people, embedded in a context defined by people. Biases, gaps, blind spots, all creations of humanity. It is a choice, sometimes conscious, sometimes unconscious, embedded in the systems we create. Artificial intelligence can help us see further, but it won't solve the fundamental problem. We search for patterns in a universe that is indifferent to whether we find them. The universe does not optimize our efforts to detect. It does not make everything easier. Objects appear from awkward angles at inconvenient times, with characteristics that do not match our training data. They hide in the sunlight, appear in bad weather, their behavior is unpredictable, and our detection systems, both human and artificial, must adapt to this reality or fail. The task is not only to create the best tools, but also to establish effective interaction between the tools and the people who use them. Next, we will examine another study in the field of neurobiology concerning spatial memory and aging as a metaphor for the degradation of detection systems over time. The 14th part, a metaphor for the degradation of tools and sensors, spatial memory and aging at Stanford. On October 3, 2025, researchers from Stanford published results on the decline of spatial memory in the elderly, studying neurons in the hippocampus, the area of the brain responsible for forming cognitive maps of the environment. These maps are not abstract. They are neural representations of physical space formed through experience and repetition. In young animals, these neurons activate reliably when the animal is in a specific location. The activity pattern is clear, constant, and reproducible. Cell A activates when the animal is in the first corner, cell B when in the second corner. This pattern creates a mental map, a neural coordinate system allowing the animal to know where it is and how to reach its desired location. But in older animals, neurons fire less reliably. Cell A may activate in the first corner, or the second, or not activate at all. The map becomes unclear, places merge, the animal still understands that it is somewhere, but this somewhere becomes imprecise. Navigation becomes more complicated. The animal wavers, retraces its steps, makes wrong turns, ultimately reaches its goal, but the path proves ineffective and dubious, with mistakes that a young animal would not have made. The study traces the mechanism of this decline. Certain proteins accumulate with age, binding to synaptic receptors and reducing plasticity. Synaptic plasticity is the ability of connections between neurons to strengthen or weaken based on experience. This is the physical basis of learning and memory. When plasticity decreases, neurons lose the ability to update the map, correct errors, and assimilate new information. As a result, the representation of space deteriorates. The map exists, but it is outdated, inaccurate, and unreliable. The animal is still orienting itself, but less accurately. It makes more mistakes and takes longer to find targets. The decline happens gradually, initially barely noticeable, but measurable. Over time, the errors accumulate and the map deteriorates. This discovery is more than just neurobiology. It is a metaphor for every detection system we have ever created. Telescopes age in the same way. Tools that were originally clear, precise, calibrated to catch the faintest signals. But over time, they lose their properties. The optical setup shifts. Mirrors focusing the light of stars are mounted on mechanical structures that expand and contract with temperature changes. Over months and years, minor shifts occur. The focus softens, and the image blurs. The light that should focus on a single pixel scatters across several. The function of point scattering, a mathematical description of how a telescope displays a point source, expands. The resolution deteriorates, mirrors accumulate dust, even in the best observatories and even in enclosed spaces. Dust scatters light, reducing the amount reaching the detector. The worst part is that some telescopes are affected by the environment. Wind brings in sand particles. Temperature changes cause condensation. Over time, the mirror's surface oxidizes. Aluminum coatings designed for creating reflective surfaces deteriorate. Reflectivity drops from 98% to 95%, and then to 90%. Each percentage loss means fewer captured photons, leaving dimmer objects unnoticed. Ultimately, the mirror needs to be disassembled and re-illuminized, a process that takes weeks and costs hundreds of thousands of dollars. Sensors develop defects. Charge-coupled devices, silicon chips that convert photons into electrons, accumulate damage from cosmic rays. High-energy particles strike a silicon lattice, displacing atoms into place, creating hot pixels that capture full signals. Dead pixels appear, areas where photons hit, but the signal is not recorded. Noise patterns emerge, systematic errors that need to be accounted for in image processing. The sensor continues to operate, but its dynamic range is narrowing. Sensitivity is decreasing. Objects at the edge of detection, those that produce only a few photons per exposure, disappear beneath the noise. Calibration becomes less precise. Each telescope requires regular calibration to convert raw detector data into meaningful measurements. You aim the telescope at stars of known brightness, measure the signal, and build a calibration curve. But the calibration shifts over time. The detector's response changes, optical transmission varies, and the atmosphere alters. If you don't recalibrate frequently, your measurements become unreliable. An object you consider a 6th magnitude star may actually be a 5th, 8th, or 6th second magnitude star. This uncertainty accumulates, brightness estimates become less reliable, orbital predictions that depend on brightness become less accurate. The inaccuracies increase, images become blurred, the detection threshold rises. Objects that were once visible, that once provided clear and confident signals, are now on the verge of statistical significance. Is it a comet or a noise peak? Is it a moving object or a hit from a cosmic ray? The uncertainty grows, and the observers become less confident. Additional observations are needed, but telescope time is limited. If every uncertain detection requires confirmation, the system starts to lag. The queue grows, objects disappear before they can be confirmed. We miss them. Service helps, but only to a certain extent. Mirrors can be cleaned, dust can be removed with careful wiping or blowing with compressed air. But cleaning poses a risk. A scratch, a stain, residues left behind can worsen the situation. Reanodizing restores the reflective properties of the mirror, but it requires removing the mirror, sending it to a special workshop for coating, waiting several weeks for the process to finish, and then reinstalling and adjusting it. During this period, the telescope is not working, observations are suspended, and research is frozen. Objects that could have been discovered during this time are completely missed. Sensors can be replaced. New devices with improved quantum efficiency, lower noise levels, and a wider dynamic range are available, but replacement is expensive. One sensor can cost millions of dollars. The setup requires precision. The detector must be cooled to cryogenic temperatures to reduce thermal noise. The cooling system needs maintenance, leaks can occur, pumps fail, and systems shut down. Even with the new detector, the rest of the optical system continues to age. A telescope is only as good as its weakest component. Calibration can be repeated. Theoretically, it is done every night using standard stars to check the 0 point and measure attenuation. In practice, clouds interfere, graphs shift, automatic systems use old calibration files, and the shift goes unnoticed until someone checks and realizes the measurements are incorrect. By that time, weeks or months of data may be compromised, and the orbits calculated based on this data will contain errors, leading to incorrect determination of object locations and forecasting mistakes. However, maintenance requires resources. Time, money, expertise, and budgets are limited. Funding organizations prioritize new projects over the upkeep of old ones. As soon as the telescope is built and put into operation, enthusiasm wanes, headlines shift to other topics, the scientists who developed it retire, the engineers who built it move on to other projects, and the institution is left with an outdated system and a shrinking budget. Maintenance is delayed, updates are postponed, the system ages faster than it can be repaired, entropy wins. A Stanford study shows that even biological systems capable of self-repair and constant regeneration still degrade with age. Neurons lose their function despite the brain's ability to create new synapses, cut unused connections, and reorganize neural networks. The hippocampus is one of the few areas of the brain where new neurons are formed throughout life. Neurogenesis continues even in old age, but despite this regenerative ability, spatial memory deteriorates. New neurons do not fully compensate for accumulated damage, synapses weaken, proteins accumulate, and maps become unreliable. Degradation occurs more slowly than without regeneration, but it is inevitable. Our astronomical instruments do not have this luxury. They cannot self-repair. They do not regenerate. Once damage occurs, it remains until someone intervenes. The intervention proves to be lengthy, costly, and often incomplete. A mirror cleaned today will be dusty again tomorrow. A sensor replaced today will accumulate hot pixels by next year, and a calibration done today will drift in a month. Degradation is relentless, and its pace is faster than biological systems because they lack an inherent repair mechanism. When tools degrade, we lose important objects. The case of Comet R2 demonstrates how detection failures occur. The comet was discovered late because it was in a geometric blind spot hidden from sunlight. However, blind spots are not always geometric factors. Sometimes they are instrumental. A faint comet at the edge of detection may be visible to a new telescope with an upgraded mirror and new detector, but the same comet observed months later with the same telescope, after dust accumulation and pixel failure, may become invisible. The object has not changed, but the telescope has, and due to the degradation of the instrument, detection does not occur. The same object observed with the same technique yields different results depending on the state of the instrument. This is not a hypothetical problem. It is reality. Telescopes for surveys have detected fewer objects in recent years than in their early days, even though the sky hasn't changed. The decline is attributed to aging equipment, optical degradation, and sensor failures. If we do not take this into account, if we do not conduct regular checks and calibrations, if we do not monitor the tool's performance over time, we start missing objects that we used to catch. We do not realize that we are missing them because they do not appear in the data. They become invisible ghosts, unnoticed, unknown. There is also fatigue from data, another form of degradation. Telescopes generate vast amounts of data. Modern wide-field surveys produce petabytes of data each year. Each image contains millions of pixels, and each pixel holds a measurement. Processing this data requires the use of pipelines and automated software that identifies sources, measures positions, calculates magnitudes, matches with catalogs, and marks anomalies. Pipelines operate continuously, absorbing new data and producing results. But as the load increases, the pipelines expand and processing time grows. Cues form, and data accumulates. An image taken tonight can only be processed tomorrow or next week. By the time the anomaly is noted, when a person looks at it and decides further study is necessary, the object has already vanished. The observation window is closing, and we lose the ability to confirm, clarify the orbit, and assess the risk. Data storage is another bottleneck. Petabytes require infrastructure, hard drives, servers, cooling systems, redundancy, and backups, all of which cost money. When budgets are cut, storage costs decrease. Old data is archived on slower media like tapes, which take hours to access. If old images need to be reprocessed or a weak object missed the first time needs to be found, one must wait. You send a request, waiting for the tape to load, data transfer, and processing to complete. Days pass, the object disappears. Vigilance requires maintenance, not only hardware, but also software, procedures, and institutional knowledge. There are errors in the software, assumptions built into the pipelines. The threshold set 5 years ago may no longer be suitable. The sky has changed, light pollution has increased, and the number of satellites has grown. The number of trails and flashes in each image has increased. The pipeline marks them as anomalies. The queue fills with false alarms. Real anomalies are lost. Adjusting the threshold is not easy. If changed too much, real objects may be missed. If too little, false alarms will keep appearing. Someone must oversee the pipeline, adjust parameters, and test results. This person must have expertise, experience, and institutional knowledge. Astronomers retire. Engineers move on to other projects. The people who designed the system understand its features, know where the blind spots are, remember why certain decisions were made, and leave their positions. Documentation helps, but it is never complete. Nuances are lost. New employees arrive and learn the system, but lack the intuition that comes with years of experience. Mistakes happen. A parameter is changed without understanding the consequences. A calibration file is updated incorrectly. An assumption is accepted that was previously disputed and rejected. The new team does not know the history. They repeat old mistakes. The system is drifting from optimal performance, detection levels are dropping, and no one notices until someone conducts a retrospective analysis and discovers that the telescope is missing objects it should have caught. The parallels between aging brains and systems are strikingly accurate. Both start with high efficiency, gradually deteriorate, lose sensitivity, and miss signals. Both require active maintenance to slow down their decline, and ultimately, they both fail despite all our efforts. The solution is the same: updating, reconfiguring, modernizing, replacing old components with new ones, preparing the next generation, documenting everything, creating institutional memory, fighting entropy at every level, knowing that victory is never permanent, but hoping to delay the inevitable long enough for it to matter. Researchers from Stanford showed that blocking age-related proteins in mice restores some spatial memory functions. This intervention did not make old mice young. It merely made them less old, slowed down decline, and bought time. This is exactly what telescope maintenance does. It doesn't restore them to factory condition, but slows down degradation, providing time to discover the next object, the next unexpected visitor, the next object hidden in bright light or at the edge of sensitivity. Time is the most valuable resource. When systems fail, when detection weakens, when degradation prevails, we lose time. And losing time means losing the chance to see what is approaching before it happens. Next, we will summarize, discuss what will happen next, what to pay attention to, what to demand, and how it all relates to the office and the asteroid that we know is approaching in 2029. Part 15, a global overview of what to watch next in the mission roadmap if R2 is an alarm signal. Here is our further plan. The comet will approach Earth on October 20th, 2025 at a distance of 0.26 astronomical units. This is just 8 days away. Between now and that time, here's what needs to be done. First, updates on R2, tracking the trajectory, refining the orbit, observing perturbations. Gas emissions create non-gravitational forces. If the comet shows activity again, if the ejection is asymmetrical, the trajectory will change, albeit slightly, but possibly enough. Continue measurements, refine the data. Do not consider the current decision final. Secondly, spectroscopy and radar. We need to know what R2 is made of. Spectroscopy reveals the composition of the coma, the gases emitted, and the molecules present. Radar, if the comet approaches closely enough and we direct the right antennas, can resolve the nucleus, measure its size, detect rotation, and possibly even see its structure. This is not just scientific curiosity. The composition affects the behavior of the comet. Cores, rich in volatile substances, are more active, and the structure influences the risk of fragmentation. If the core is a pile of debris loosely bound together, it may break apart. If it is a solid monolith, it will remain intact. We need to know which option is correct. Thirdly, high-resolution images. Try to resolve the core. Attempt to detect fragments. If R2 has cracked, if pieces are scattering, we need to see it now while there is time to track their trajectories. The fragments initially spread slowly. The sooner we notice them, the more accurately we can predict their movement. Fourthly, monitoring dust and debris. Look for traces. Look for emissions. Look for meteoroid activity. Ground cameras can detect particles entering the atmosphere. Satellite sensors can measure the flow of micrometeoroids. If R2 drops debris, if Earth approaches a debris stream, we need a warning. Even a few hours of warning is enough to switch satellites to protective mode, orient solar panels edgewise, and reduce cross-sectional area. Fifthly, modeling dangers for spacecraft. The International Space Station is at an altitude of about 400 kilometers. Satellites occupy various heights from low Earth orbit to geosynchronous at 36,000 kilometers. All can become potential targets. A dense stream of meteoroids increases the risk of collision. The risk is still low, but low is a relative concept. If the background flow is 1 particle per million cubic kilometers per hour, and the debris flow increases it to 10 particles per million cubic kilometers per hour, that's a 10-fold increase. Small numbers multiplied by large volumes and long durations add up. Model the flow, assess the risk, prepare contingency plans. Now about politics and systems. What should we demand from the institutions that are supposed to protect us? Firstly, it is necessary to invest in a solar observation system. Most of our telescopes are directed away from the sun, which is natural since its brightness dazzles the sensors. However, objects approaching Earth from the solar side remain invisible until they appear on the screen. We need space telescopes that will monitor the sun, as well as ground instruments capable of detecting comets and asteroids in bright light. Who proved that this is possible? We need more tools specifically designed for comet detection, covering a wider range. Secondly, public real-time data transmission channels are necessary. Transparency reduces the vacuum for conspiracy theories. When observations are published immediately, when orbital solutions are updated in real time, when uncertainties are clearly communicated, the level of trust increases. People no longer have to guess when data is available. The Center for Small Planets and the Rocket Motion Laboratory are already doing this to some extent, but the interfaces are too technical. We need open control panels, visualizations, simple language summaries. The data must be accessible and understandable. Thirdly, international coordination is necessary. Telescopes are scattered across the world in different time zones, covering various parts of the sky with different capabilities. A network, coordinated in real time, can constantly track objects. When one telescope loses an object over the horizon, another picks it up. Alert protocols must be standardized. If one observatory detects a potential threat, how quickly will that information reach others? How fast will it reach decision makers? Minutes matter, hours are important, days are critical. Let's consider the example of an asteroid named Apophis. Its diameter is approximately 340 meters, and it will pass closer than geostationary satellites on April 13th, 2029, which is less than 4 years from now. We have known about Apophis since 2004, tracking it for 21 years, precisely knowing its orbit and location on April 13th, 2029, within a kilometer. We are confident that it will not collide with Earth. Its trajectory passes at a distance of about 31,000 kilometers, closer than some satellites, but still safe. We have time to prepare and set up instruments for its study during the flyby. Apophis is a predictable case, one we anticipated, one we can observe in slow motion. In contrast, R2 is the complete opposite, unpredictable, a late discovery, uncertain orbit, unknown composition, possible fragmentations. R2 is a case that frightens risk assessment analysts, not because it will confront us, but because we almost did not notice it, and there are many such objects that we have not seen and will not see until it is too late. The difference between Apophis and R2 is time. Apophis gave us decades, R2 just a few weeks. Time is the most important resource in space defense. Time for observations, time for trajectory adjustments, time for option assessments, time for actions. When time runs out, opportunities vanish, and all that remains is to watch, hope, and pray that the numbers stay stable, that uncertainties do not worsen, that fragments do not drift into orbits crossing the Earth. Predictable large objects attract attention. Comets and asteroids will be studied in detail, with all telescopes and radars directed at them. We will learn more about asteroids from one close encounter than from decades of distant observations. This is good, but the risk lies in those objects we do not notice. Small, quick, unexpected, radically unknown, those that hide in bright light and appear from unexpected angles, those that suddenly become visible when we turn away. It is they who can catch us off guard. The universe does not try to destroy us, nor does it strive to save us. It is indifferent. Objects move through space following the laws of gravity and momentum. Some cross our path, most pass by, some collide. The distribution of these events is statistical, random over short time spans, predictable over long ones. We live in a short time window where collisions are rare enough for civilization to exist, but frequent enough that we must monitor the situation. The impact object that ended the age of dinosaurs 66 million years ago had a diameter of 10 kilometers, moved at a speed of 20 kilometers per second, and released energy equivalent to billions of nuclear warheads. He dug a crater 200 kilometers in diameter, hurled debris into the stratosphere, darkened the skies, and ended an entire era. This could happen again. Not today, not tomorrow. Likely not in our lifetime. But in the end, the question is whether we will see it in advance, whether we will have time to take action, build systems, develop technologies, train people, coordinate institutional actions to respond to the threat, or if we will be like dinosaurs, unaware of the impending disaster until the sky catches fire. Our case will not become such an event. It is too small, too distant, and well monitored. But this is a test of our detection systems, a test of our communication systems, a test of our ability to respond to uncertainty with rationality rather than panic. So far, we are managing. The comet is being tracked, the orbit is being refined, the risk is reported, no one is panicking and they shouldn't, but we must pay attention. Not to the spectacle, not to the sensationalism, not to conspiracy theories or disasters, not to opinion manipulators, but to the gaps, blind spots, detection failures, institutional bottlenecks, what we miss because we are looking the wrong way at the wrong time with the wrong tools. These are lessons. This is what matters. Look at the sky, demand better observation systems, question narratives, maintain curiosity, stay skeptical. The universe is full of wonders and dangers. Most often, wonders are safe, but dangers do not announce themselves. They do not wait for permission. They just come. And when they come, the only thing that stands between us and disappearance is the quality of our detection systems and the speed of our response. 8 days until the nearest approach, Object R2 is already on the way. We are monitoring it. The numbers say we are safe, but numbers are not always accurate. They represent probabilities dressed in equations, and these probabilities sometimes surprise us. This is why we observe, why we make calculations, why we create telescopes, train astronomers, conduct interesting surveys, and coordinate actions internationally. The alternative is ignorance, and ignorance is the only thing more dangerous than the objects themselves. Space is not empty. It is filled with debris, fragments, and wandering objects. Most pass by without consequences, but some do not. R2 reminds us that our environment is not so quiet, that movement is real, the risk is small but never zero, and vigilance is not paranoia, but a matter of survival. Keep watching.